In this video, we're going to talk about limit strategies you can use when you realize you have a limit with an indeterminate form. I'm focusing on indeterminate forms here because if it's not indeterminate, you can often find the limit by either direct evaluation, just substituting in the value, or by realizing you have, say, something like 0 or infinity, which is going to evaluate to 0, or infinity over 0, which is going to evaluate to infinity, etc. So these are all these examples, all these strategies are for indeterminate forms. So the first sort of category of strategies is algebra. Of course, feel free to pause this video, write these problems down, and then kind of come back when you're ready to take notes. These notes, by the way, should go in your regular notebook, not in your ISN. Okay, here we go. So under algebra, probably the most straightforward strategy to use when you recognize you have an indeterminate form is if it's factors. So this first example here, let's zoom in. So if I directly substituted 2 to the third minus a to 0, 2 squared minus 4 is 0, so we have 0 over 0, which is an indeterminate form. So one thing we can do is recognize that both of these expressions factor. So x cubed minus 8 is a difference of cubes. If you don't know that formula, just go Google it. So a difference of cubes factors as a cubed minus b cubed is a minus b times, and the only reason I happen to know this is when back in the day when I took trig, my teacher had this up on the wall and I would stare at it when I was bored in class. All right, so a minus b times a squared plus ab plus b squared. All right, so I'm just gonna replace the a and the b with the 2 and the x. So x, 2x, 2 squared, I'll just make that be 4. So again, and then the denominator, that's just a difference of squares, so that would factor as x minus 2 times x plus 2. Okay, so by factoring this, what we notice is if you substitute a 2 in now, x minus 2, we have 0 times something that's not 0 over 0 times something that's not 0. So if you cancel these two parts that are going to 0 at the same rate, as x approaches 2, both of these will approach 0 at the same rate because they're identical. So if you cancel sort of the zero-ness in the numerator and denominator, what you're left with is something that can be evaluated directly. And you see what was like hiding behind the zeros. It was 0 times a value over 0 times a value. If we cancel those two zeros that were identical, we see that in the numerator we have 2 squared plus 2 times 2 plus 4. So we have 12 over 4 or 3. So this reveals that once the parts that were approaching 0 cancel, we're left with a 3. So that's kind of why factoring is a nice strategy. It's pretty clean. All right, the second example, multiply by the conjugate. If you ever encounter a problem, particularly if there's a square root in a binomial, so like here we have a square root expression minus 2. If you see two terms and one of them is a square root, strongly consider if it's indeterminate multiplying by the conjugate. And in this case, if we directly evaluate it, we can see it is indeterminate. If I plug in a 2, square root of 4 minus 2 is 0, 2 minus 2 is 0 in the denominator, I get 0 over 0. So what I'm going to do is multiply by the conjugate of the part with the square root. So that would be 2 plus x plus 2. So the conjugate is just, I take that symbol in between and flip it. I have to multiply both the numerator and denominator by that conjugate. And so I get, please notice I'm writing the limit every time. That is absolutely required. You cannot be lazy and not write the limit statement and have it be mathematically correct. All right, so then if I multiply these two conjugates together, this is basically a minus b times a plus b. When we multiply a minus b times a plus b, we get a squared minus b squared. So I get 2 plus x, because that's, and then minus 2 times 2, 4. Okay, over, and now this is going to be messy, but that's okay. We're going to trust the process here. And then this is square root of 2 plus x plus 2. So multiplying by the conjugate is a little bit of a leap of faith that it's going to work out. All right, so if we look at the numerator, 2 plus x minus 4 simplifies to x minus 2, and now we see something beautiful. So there's an x minus 2 in the numerator and denominator, and as x approaches 2, those are the things that are going to approach 0. So if we cancel those zeros, we see what's lying underneath. So I'll cancel those in red. And so I'm left with 1 over square root of 2 plus x plus 2, and that evaluates to 1 over square root of 4, 2 plus 1/4. So hiding under the 0 in the numerator and denominator was a 1 and a 4. So this is going to approach 1/4. So that's the method of multiplying by the conjugate. And then the last one is the one we use probably the most frequently. So once you can see that whole row. Dividing by the numerator and denominator by the highest power of x that's in the denominator. Okay. This is one where sometimes students see these problems and go, oh, I'll just do L'Hopital's rule, and then I jump up and down and go, no, 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 don't do that. That's so much harder. I have got a lot of noises going on here. All right, so what we're going to do is multiply the numerator and denominator by the reciprocal of x to the third. Okay, apparently I did not put on do not disturb. Good Lord. So I'm going to multiply the denominator by 1 over x to the third and the numerator by 1 over x to the third. Okay, because that's the highest power of x in the denominator. Let's look at what happens when I do this. Oh, I forgot. I should have said why I know this is indeterminate. As x goes to infinity, the numerator is going to go to infinity. The denominator is going to go to infinity. So it's an indeterminate form of infinity over infinity. But if I do this little manipulation and distribute that 1 over x to the third, I get 1 over x plus 3 over x to the third over 1 plus 2 over x squared plus 1 over x to the third. Now, why is this a good thing? Because almost all of these are now going to go to 0. As x goes to infinity, that's going to go to 0. That's going to go to 0. This is going to go to 0, and this is going to go to 0. You do not have to write the part in red when you do the work. This is just me showing my thinking. So this is going to go to 0 over 1, which is just 0. Okay, so just did that with algebraic manipulation, no fancy L'Hopital derivatives, stuff like that needed. Here's another, I wanted to do this example because sometimes you also see it with root expressions. So again, as x goes to infinity, that numerator is going to get infinitely large, the denominator is going to get infinitely large, and so this is going to go to infinity over infinity. But if I recognize the highest power of x in the denominator is x squared, so I'll divide the top and bottom by x squared. And let's look at what happens. Again, notice I'm writing that limit every single time. Absolutely necessary to do that. Will I take points away if you don't? Yes, I will. All right, so the denominator, if I divide everything by x squared, I get 1 plus 1 over x squared. Now the numerator takes a little more of a manipulation because 1 over x squared is not in the square root, so you can't distribute it into the square root until it is. So what I do is I sometimes think about it like this. I'll put it in a square root, and then I'll double the power. Okay? Because square root of 1 over x to the fourth is the same as 1 over x squared. All right, so now that it's in a square root, I can distribute it, and I get x plus 3 over x to the third. And so then again, we can notice this is going to go to 0, this is going to go to 0. So I'm going to be left with the numerator going to infinity and the denominator going to 1. So infinity over 1, that's just going to be infinite. So what we discovered here, what we proved essentially with our steps here, is that the numerator is going to infinity faster than the denominator, whereas in the example above, the denominator is going to infinity faster. Okay, but we just did that with an algebraic manipulation. Now, you might be wondering, well, can I just recognize that the power in the denominator is larger or smaller than the power in the numerator and jump right to the answer? And the answer to that question is no. What you're doing essentially here is you're writing a proof. Okay, so the steps that we're showing here is you're proving why it comes out to 0, or why it comes out to infinity, or why it comes out to some other value. So these steps are a necessary part of the proof. Okay, so you can't just jump to the answer because you can do it in your head. I can do it in my head too. I still write out all the steps because I'm creating a proof for the reader. All right, L'Hopital's rule. This is one of the most well-known ones, but we want to talk a little bit about why it's working. So L'Hopital's rule can be applied for two indeterminate forms, 0 over 0 or infinity over infinity. I suppose it could be plus or minus infinity over infinity. Okay, so only those two forms. So if you have some other indeterminate form, can't use it. So this one, as x approaches 0, sine 5x over x. Well, 5x, sine of 0 is 0. So this is going to approach 0 over 0. Okay. So we're going to apply L'Hopital's rule. And we're going to take the derivative of the numerator and the denominator. That's how L'Hopital's work. Let's talk a little bit about why L'Hopital's rule works. So these both are going to 0, and we said 0 over 0 is indeterminate because we don't know if the 0 in the numerator is getting, the value in the numerator that's approaching 0 is getting small, faster, or slower than the one in the denominator. When I use the word faster or slower, what you should immediately think of is that that's a rate. And we want to compare the rates at which they're approaching 0. And a rate in calculus is a derivative. So by taking the derivative of the top and the bottom, we're going to be then comparing the rate at which those two values approach 0. So let's do it. So the derivative of sine 5x, derivative of sine is cosine. But then I have to apply the chain rule. Derivative of 5x is 5. And then derivative of x is just 1. Okay. So the x is approaching 0 at basically a constant rate. The sine 5x is approaching at 0 at a non-constant rate. So let's now evaluate this. So if now I substitute 0, cosine of 0 is 1. So this is going to be 5 over 1 or 5. So what we've discovered is that the numerator is, hang on. I'm trying to think if it's correct to say the numerator is approaching 0 faster or slower than the denominator. Well, let's put a pin on that. We can come back to that. I'm having a moment. All right, let's look at this second example. So limit as x approaches infinity of e to the x over x squared. So if I thought about sort of what happens as x goes to infinity, e to a very large power is going to approach infinity, and a very large number squared is also going to approach infinity. So I have infinity over infinity. And so what you should do is get in the habit of saying, yep, this is going to go to infinity over infinity. Please notice I used an arrow there and not an equal sign. An equal sign is incorrect because 0 over 0 or infinity over infinity is not a value, so you can't say it equals. Okay. So I generally use an arrow there to be mathematically correct. You should too. The AP test will not like it if you write equals infinity over infinity. You could potentially lose points. All right, now, between you, me, and the lamppost, if I look at e to the x over x squared, I know that exponentials get much faster than polynomials. So if you think of the graph of e to the x, it's going to grow much quicker than x squared in the long term. So I know that the e to the x is going to grow quicker than x squared. But you can't just, that's not a justification. And what we're doing here is writing proofs. So we need to sort of prove that e to the x is growing faster than x squared. And so I'll just write down, okay, I'm going to apply L'Hopital. This is a good habit to get into. Just write down, this is what I'm doing. And so then I would get the limit as x approaches infinity. Derivative of e to the x is e to the x. Derivative of x squared is 2x. Okay, still infinity over infinity. So we're going to apply L'Hopital's rule again. Derivative of e to the x is e to the x. Derivative of 2x is 2. So now the numerator will go to infinity and the denominator will go to 0. So comparing the rates of the two, I still got infinity over infinity, but in comparing the rates of the rates, then I finally got that the numerator was growing much faster than the denominator. Okay? So that's kind of how to show your work with L'Hopital's rule and why it works. We're comparing how quickly are the numerator and denominators approaching either 0 together or infinity. Okay, so then the last kind of problem is if you have one of these indeterminate forms with a power. 0 to the 0, 1 to the 0, or infinity to the 0. All right, so let's check these out. So the limit as x approaches 0 on the right of x to the sine x. Well, let's look at what happens. So the denominator will approach 0 and be positive. The numerator will also approach 0. So this is definitely an indeterminate form. Again, notice I used the arrow. So what we're going to do when we have one of these exponential indeterminate forms is we're going to take the log. So this isn't going to equal. This is doing a different limit. But I'm going to take the limit as x approaches 0 on the right of the natural log of x to the sine x. Okay, logs are really useful, and this is a great example of a time when they're really useful. And then we'll rewrite it with the log rules. So one of the biggest utilities of logarithms is that they can get things out of the power. The power property of logarithms says that can go in front, and I would have sine x times the natural log of x. Okay. Now we have a little bit of a problem because sine x will approach 0. And natural log of x, if you think about the graph of natural log, it looks like this. So as we approach 0 on the right, natural log is going to approach negative infinity. So this is still an indeterminate form. We haven't solved that, but we can do a little trick here. So what I'm going to do is rearrange this so I can apply L'Hopital's rule. Because 0 times negative infinity is not a situation for L'Hopital's rule. But if you rewrite it as the natural log of x over, so if I want to move sine to the bottom, I'm going to get 1 over sine, which is cosecant x. Okay. All right, now that, shouldn't have used an equal sign. The natural log of 0 is going to approach negative infinity. Cosecant x is also, hang on, from the right, is going to approach positive infinity. So I've got L'Hopital's rule. So this one's going to take a lot of room, I'll warn you. So then this would equal, so the reason I took the product and rewrote it as a quotient is so that I would get a situation where I could take the derivative of the numerator and denominator separately. Derivative of natural log of x is 1 over x. Derivative of cosecant x is negative cosecant x cotangent x. Okay. Limit as x heads to 0. Right. So let's say this would be 1. X would go on the bottom. Cosecant is 1 over sine, so I could put a sine on the top. And cotangent is cosine over sine, so I could put a cosine on the bottom and a sine on the top. So I'm doing that just to think about what's going on. So if I rewrite this, then the denominator cosine of 0 is 1. So this is going to go to 0 in the denominator and 0 in the numerator. Okay. But I think I can apply L'Hopital's rule again. So if I apply L'Hopital's rule again, derivative of sine squared x is 2 sine x. Because I take the power in front and reduce the power by 1 with the power rule, but then I have to take the derivative of sine, which is cosine. All right, the bottom I got to do the product rule. Derivative of x cosine x is cosine x plus x. Derivative of cosine is sine x, and of course I have to change that plus to a minus because derivative of cosine is negative sine. All right, let's see if we've done anything useful here. The numerator is going to go to 0. The denominator is going to go to cosine 0 is 1. Hey, this is useful. Look at this, because I got 0 over 1 minus 0, so I didn't actually need that arrow. I could have said equals. So this equals 0. Okay. And then you might think, oh my god, I just did so much algebra, I'm done. But you're not. So what we just did is found that the natural log of this expression approaches 0. So how do we undo a natural log? By doing e to a power. So the limit as x approaches 0 on the right of x to the sine x is e to this answer, which is just e. Okay. This was a lot, and you probably have some questions, so please jot down at the end what questions you have after watching this video, and we can talk about them in class tomorrow. Okay.